Okay, let's do the review for Unit 9. So this guy right here is the slope, right? So let's write that as a fraction. So negative 3.2088 divided by 1. And let's think about what is our x and y here. So x is our runtime. So that's always the x variable right there in the output. Let's think about what the y is. I guess this is oxygen consumption. Okay, so runtime, I didn't look for what the unit is, runtime in minutes. And then this is oxygen consumption measured in, I don't know what it's measured in. Okay, so let's see which one does this. So this one's increasing and this one's decreasing for every 1 minute of runtime. An increase in runtime of 1 minute decreases the predicted oxygen consumption by, well, that sounds pretty good. I just want to make sure. An increase in oxygen consumption of 1 minute decreases. No. An increase in runtime, 1 minute increases, predicted oxygen consumption increases. No, that's not increase. That doesn't make sense. Runtime of 10 minutes corresponds. I don't think that seems right. Okay, so it's got to be age. I mean, it's just, if you think about it as a fraction and think about it in context, it should make sense. In a study of the performance of a computer printout, okay, the size in kilobytes and the printing time in seconds for each 22 small text files were recorded. The relationship between the file size and the printing time was approximately linear. I guess that makes sense. The results of the regression analysis are shown below. Which of the following represents the margin of error? So again, if you think about, your slope, so it'd be b plus or minus t critical value times the standard error, right? So this part of it is the margin of error. So we need to find the t critical value for this guy. So 95% confident, so 0.95. This is 0.025. So you go to inverse t of 0.975. And degrees of freedom would be, I guess, 20. So you get out your calculator. Inverse t of 0.975 comma 20 is 2.08. So we know it's one of these guys. And, well, we know this is the standard error is this guy. So the slope is this guy. The standard error is right next to it. So SE. So it's got to be that one. Dissolved oxygen is important for the survival of aquatic life. Researchers measured the concentration of dissolved oxygen in Lake Champlain at various times and depths. They also recorded the temperature for each measurement, 14 computer output for linear regression of those two things, sample of 500 measurements. Okay, so that's all the computer stuff. They give us the confidence interval after all that. What does the confidence interval suggest about the association between dissolved oxygen concentration and the temperature in Lake Champlain? Okay, so because all the values in the interval are negative, the interval suggests that as the temperature increases, the amount of dissolved oxygen concentration decreases on average. So that seems to be, I'm leaning towards that's true. It's a negative slope, so as one is increasing, the other one's decreasing, so that makes sense. Because 0 is not an interval, there's no difference between no, I don't think it's a test of no difference here. We're in a slope, so I don't think that's right. Correlation, so because it's close to 0, I think you're confusing correlation with this, which is different. Because 0 is not an interval, there's a difference. There is a difference again, just because that one, that doesn't make sense. Because all the values are negative, the interval suggests as temperature increases, the mountain also increases. So that would be a positive slope. I don't think that's it. So it was the first one. Sometimes you just have to read all of them. Just make sure there's not something you missed in that first one. That should be it. Can we predict annual household electricity costs in a specific region from the number of rooms in the house? Below is a computer output for the linear regression of the annual electricity costs versus the number of rooms for 30 randomly selected houses in Michigan. Which value in the computer output is the estimate from the sample and the standard deviation of the residuals? And so, like we talked about, this one is the standard error right there. This is the standard deviation of the residuals. So I think it'd just be this one. Yeah, I think that's right. Are high school students who like their English class more likely to enjoy history class as well? Oh, that's interesting. Probably. Here is a regression analysis of 30 randomly selected students who were asked to rate how much they enjoy both the English and history on a scale of 0 to 5. Higher rating means the student liked the subjects more. And it does have a positive slope there, so that's some evidence. Assuming the conditions for inference are met, which of the following represent a 99% confidence interval for the rate of change? So we see like similarities. They all start with 0.0524. That's the slope, and that's what it should start with. So we haven't eliminated anything yet. Let's definitely do this one on here. So 0.99. So this is 0.005. Degrees of freedom would be 30 random, so 28. So get your calculator out. Let's do that one. So inverse t of 0.995 comma 28, 2.763. So it's one of these guys. It's got to be that one. We don't use that formula for slopes for this. We just take the number next to it. That's the standard error. We plop it in right there. Does missing school more often tend to result in lower grades? I would say this should happen, I think. A guidance counselor selected a random sample of 30 students, recorded how many days of school they missed in the previous school year and their current GPA. Assuming the conditions for regression for inference have been satisfied, is there convincing evidence that GPA decreases as the number of days absent from school increases? To answer this question, we said, which test the hypothesis. So what's the hypothesis for this test? So we, I don't think it's going to be one of those. So there is no difference. That's the null. There's nothing going on here, nothing to see. So is there convincing decreases, the GPA decreases as the number of absent days increases. So one's increasing, the other is decreasing. That would be a negative slope. So I think it would be B. Are high school students who like English class more likely to enjoy their history class as well? I think we just did this one, but different question. Assuming the conditions for inferences are met, we wish to perform the test where beta equals 0 for the regression slope, but the test statistic did not print properly in the output. What is the test statistic for, oh, it didn't print properly. It's funny, there's a bunch of X's there. Okay, well, I forgot what to do here, right? So T equals, it's going to be the slope, 0.5254, technically minus the null, which is 0, over the standard error, 0.1995. So that should give us, that is a funny question. It just didn't print properly. That's what happened. 0.5254 over 0.1995. 2.6, there you go. So it should be that guy. A college professor wants to know if it is possible to predict the grade students will earn in their final class, on their final, from their class average just prior to the final. So would the class average kind of predict their final? She selected a random sample of 15 students, records their average just prior to the final, as well as the grade they earned on the final. Assume the condition for regression inference have been satisfied. To construct a 90% confidence interval for the true slope of the population regression line, relating to the final exam to prior class average. How many degrees of freedom does the t-distribution have? So 15 students, so degrees of freedom is n minus 2. I got it. Swimming and pulse rate. Professor Moore recorded the time in minutes he took to swim 2,000 yards at his pulse rate in beats per minute after swimming in a random sample of 23 days. Does his pulse rate tend to be higher on days that he swims faster, has smaller times? Some computer output from a least squares regression line is shown here. Assume the conditions are met. Calculate the test statistic. Okay, so again, t equals the slope, which is negative 9.6949 minus the null over 1.8887. So let's get that first. So negative 9.6949 over 1.8887. So negative 5, so it's one of these guys. And then if you've got, so zeros here, negative 5.133. So we're shading this way, I would think. So this is going to be inverse t negative infinity, comma, negative 5.133, comma, degrees of freedom, which is 21. Inverse t, it's TCDF, sorry. TCDF. We're trying to find the area under the curve. Oh, wow. 0.0000, wow, there you are, go. That would be it. Because I think this was a 1, let's just make sure. Make sure it's in one direction. He took a swim 200 yards. Does his pulse rate tend to be higher in days he swims faster? So higher pulse rate, smaller times, faster. So that's a negative slope. So that should be right. It's one direction, it's not two. A statistically minded English teacher wonders if she can, is there such a thing? If she can predict the lengths of essays that her students submit on the basis of how large the computer files the essays are. She selects a random sample of 13 student papers, all produce the same word processing software, and compares the file size in kilobytes to the word count for each. A computer regression analysis of the data is given below. Assume all conditions for inference for slope have been met. The teacher uses this data for the hypothesis that for those things, ooh, interesting, the alternate is not equal to, so you have to double that p-value if you do it by hand. Which of the following is appropriate conclusion? Well, it tells us the p-value right there, and that's for this type, that's double-sided, so we know it's one of these. We do not, yeah, we do have convincing evidence, it's got to be A. Ooh, that was nice. Okay. 11 looks like a long question here. So Professor Brady asked a random sample of 10 of his 250 students in her introductory stats class to record the total amount of time they spent studying for a particular test. It also recorded the score of the test. Then she performed a regression analysis for the data. You can see it seems like maybe a positive correlation here. Use a computer output to discuss whether the conditions have been met. So L, linear, check, because the scatter plot looks somewhat linear and the residual plot is scattered. It fits that. I is independent, and I would say that 250 students in her class, a random sample of 10. 10 is less than 10% of 250. It's a decimal point there. Okay. L stands for a normal. This is not I was looking for this to be like a dot plot or even it's not what I'm looking for. I think we might need, I'm going to have to check that one. We might need some more information for normal. Equal standard deviation. If you look at this guy, for each x value, there seems to be no pattern for the y values. They're somewhat equally spread out. So I think that's okay. And then R stands for random sample. Yeah, that's good. So that works. Random sample. You would write random sample. I'm not sure about that. Let's check the answer for 11A. 11A. The normal probability plot, the residuals shows no strong skewness or outliers. Okay, so this is something I don't think, I'm not sure if we've even done this year, just because it's not part of the AP curriculum. So I didn't recognize it's called a normal probability plot. I was thinking it was a scatter plot. It's a normal probability plot of the residuals there. So because that does look linear-ish, we're going to say that that's okay. So it's normal. It's a normal probability plot, so it does fit it does prove that condition. So it's an unusual way to do it. It's not something we're used to. Let me just see if we did the rest of them right on that one, just because there were some weird ones. And yeah, okay, so we're good on the rest of those. Okay, part B. For the remaining questions, use the data, assuming the conditions have been satisfied. Do the data provide convincing evidence there's a linear relationship between study time and test scores? So what's it asking us to do here? I think we're supposed to do a test, right? So the null is that beta is equal to 0. The alternate is that beta is greater than 0. We think it's going to be a positive relationship there. I'm thinking it is. And then define what beta is. Beta is the true slope of the population regression line when x equals time and y equals grade for the students who in the introductory stats class. Okay, so then we're going to go to the conditions. We just checked, so we're not doing that again. So let's do the do section here. So you could do, t equals, so you could do the slope, which is 12 over the SE, which is 2.825. If you're good, you know that should be equal to 4.25 because they tell us what T is right there. That's the shortcut. And then you could do TCDF, that's 0, so 4.25 you're shading this way. Do TCDF for 4.25 to infinity with degrees of freedom at 8. However, you don't need to because it tells us the p-value is that. We just have to divide it into 2. So the p-value is equal to 0.0015. Because our p-value is smaller than our alpha level of 0.05, we reject the null. We do have evidence that what is this about? The more time you study, the better grade you will get. Okay, so I have one thing different than what they had in the answer key, and I think they're probably right. I guess I just kind of assumed it wasn't worded this way, but I was looking at the answer, seeing a positive slope, thinking to myself, don't we kind of know those things are positively correlated? Thinking the real question is there a positive relationship? But actually, is there a linear relationship is really the question. So it actually was not equal to for the alternate, which means we don't have to divide this by 2. So it's 0.003 or whatever it says up here. So it would be two-sided. So that's something they had different in the answer key than I had done. I think that makes sense because they just said, is there a linear relationship? And they didn't really give us a direction in the question there. I guess in my mind, I was expecting it to say, I don't know, it's kind of natural on this one to kind of think that there's going to be a positive relationship there, but they didn't state that, so just okay, not equal to. So good learning experience. Construct and interpret a 95% confidence interval for the slope of the population regression line for predicted test scores. So slope was 12. So 12 plus or minus. We don't have to check the conditions. We've already done that. Plus or minus the critical value. So 95. So 0.95 and 0.025. So you can go inverse T of 0.975, comma, degrees of freedom, which would be 8. So you would type that in your calculator. So inverse T of 0.975, comma 8, 2.306 times the standard error, which should be listed right here, 2.825. 2.825. Okay, so this is going to be 12 plus 2.306 times 2.825. And then subtract here. So it goes everywhere from, wait, something's wrong. Let's get rid of that one. So I added a 0 somehow. I don't know how I did that. I knew there's something wrong though, at least I caught it. So the lower bound is 5.486, comma, the upper bound is 18.515. So interpret, so we are 95% confident the interval from 5.486 to 18.515 contains the true population slope where x equals study time and y equals grade for students who are in the introductory stats class. And finally, can the teacher tell students that her data establishes that studying more will improve their grades? So how are these folks? It was a random sample. Because it was a random sample, but it was just an observational study, right? So we could generalize, but the problem is it's not an experiment. Well, it's not an experiment. Can we prove causation? We can't prove causation. Let's see what they said for 11D. So no, because this was not a controlled experiment. It was just a study. We can not establish a causal relationship between study time and test score. There may be other variables that are confounded with study time. Oh, I like using that word. Throw back to the thing. Yeah, that's the same interval we got. Good. Okay. 12. The height in feet and volume in cubic feet of usable lumber on a random sample of 32 cherry trees are measured by a researcher. The goal is to determine the volume of usable lumber that can be estimated from the height of a tree. Below is a computer output of a linear regression of the height versus usable lumber. Is there convincing evidence of a positive? So this one does have a direction to it, right? Unlike that last one. So if I'd read it carefully, I would have been like, okay, so I read this one better, so that's good. So beta equals 0, so the alternate, this is the null, this is the alternate, is that beta is greater than 0. We think it's going to be a positive slope. See-all conditions, oh, this is so nice when they say that. Okay, so this is, what's it called? It's called a t-test for slope. And so then we're going to find out what t is. T is, if you want to show off, 0.666 over 0.415. That's those two numbers divided. But we really know that's going to be 1.603. We could draw that, shade to the right of 1.603, do t-CDF of 1.603, comma infinity, comma 30 for degrees of freedom, and that'll give us our t-CDF there. Or we could divide this number by 2 because that's for a two-sided test. So we could just do 0.119 divided by 2, 0.0595. So p-value equals 0.0595. And just to show you that it works, hopefully this works, TCDF 1.603, comma, infinity, comma, 30. 0.0597. We got, so slightly different than what they had there. I trust that number better. I don't know, we'll see. P-value is 0.0597, so we don't, because the p-value is greater than the alpha level of 0.05, we don't have enough evidence. We failed to reject the null. We don't have enough evidence to say that there is a positive linear relationship between usable number and tree height for this population of cherry trees. Yeah, that's what they said, I think. Okay, great. That's your review. That's the end.